Hello and welcome back to this course. So in this lecture, we're going to be talking about gradient descent, which is the Bayes algorithm used to train deep neural networks. Okay, so this lecture is very important, so make sure that you comprehend all the concepts very well. So gradient descent is the Bayes algorithm that is used to minimize the error with respect to the weights of the neural network. So remember that we said our objective in a neural network is to reach the minimum error point, okay, which gives you a loss near to zero. So you want the difference between your actual prediction and your neural network prediction to be very close to zero. So basically what we want to do is reach this point right here. This is the minimum point of the error function. So how do we reach here is by adjusting the network weight by the backpropagation algorithm. Now the backpropagation is based on gradient descent. So that's what we're going to understand in this lecture. So I'm going to take this example where we have a two-dimensional plot. So the x-axis here are your weights and the y-axis is your loss function. Now we want to reach this point right here, okay? So how do we reach here? How do we minimize the y-axis? So we want to move down the y-axis because we want to reach here. How do we do this? Is by changing the x-axis. Now here your x-axis are your weights. So that's why we're going to need to adjust the weights in order to reach this minimum point. So let's say that our initial weights start here. Then what we're going to do is compute a gradient. We're going to compute the slope of the loss. So the slope is the differentiation of your loss with respect to the weight. So how much should we change the weight in order to reach the minimum point right here? So a slope defines the change in y that happens when you change x. Okay, so when we change the weights right here, how much is the y gonna change? Y here is your loss. So whatever we change in w, what's going to happen to y? This is your slope. So let's say that our slope is big, then we reach here faster. Now this is more into the learning rate, which I'll be talking about in the next few slides. I just want you to get the idea of this two-dimensional plot, and once you can understand what's happening here, then you can just transfer the knowledge that you have to the three-dimensional plot. Now the three-dimensional plot is basically showing you two weights. Okay, so here we consider that our neural network only has one weight, okay, such as the case in linear regression. But here we're going to consider that our neural network has two weights. Okay, so we're going to need to change W1 and W2 in order to reach this minimum point right here. Now, usually your neural network, depending on your application, has a lot more weights. So the number of weights can reach 1,000 to 1,000,000 and even over 1,000,000 in some applications. So you can't really imagine a plot with 1,000 dimensions or 1,000,000 dimensions. Okay, this is far from our imagination. However, a computer does that very well. So all you need to do here on this slide is just take the concept of how do you reach this minimum point is by adjusting the x-axis here, which is the weight. Okay. Now let's dive deep into the slope concept. So remember, the objective is to minimize the error, and how do we do this is by changing the weight. Now, how we do this is we move the direction opposite to the derivative. So this is your slope right here that I've been talking about in the previous slides. The derivative of your error with respect to the weight. Okay, so this is the slope that you're calculating. And in neural networks, it's not really called a slope, it's called the gradient. Okay, so this is one of the terminologies you should understand. So how do we compute this gradient is by taking the derivative of your error with respect to the weight. Now what we want to do is move in the direction opposite to the derivative. That's why we have a negative sign right here. Why do we do that? So if we compute a positive slope, that means we want to go left in order to reach this minimum point. And if we compute a negative slope, that means we want to go right in order to reach the minimum point. Okay? So when we have a negative slope, let's just consider the example of a negative slope. And this is a negative slope. And if you're not familiar what a negative derivative or a negative slope means, it simply means that when you're increasing x, then your y decreases. And on the other hand, a positive slope means that when you're increasing x, then y is also increasing. Okay, so let's say that our x-axis is here, then our y is somewhere here. And if we increase x, then our y is also going to increase, so it's going to be somewhere here. Okay, so a positive slope means that when you increase x, your y also increases, and a negative slope means that when you increase x, y decreases. Okay, so let's consider the example of a negative slope, which is this slope right here. So remember, our objective is to reach the minimum. So our objective is to move right in this case. So when we increase the w, the loss function is decreasing. So in order to do this, we are going to need to add the slope to our current weight. Okay, so if we're here, if we're on this current weight, then we want to make this weight bigger, so we want to add to it whatever the slope is in order to reach this minimum point. Because in order to move right, that means we're going to need to add something, which is the slope to this weight. So how do we do this? So originally we have a negative sign to the slope right here. And if your slope is negative, that means you have a negative sign right here as well. So a negative multiplied with a negative gives you a positive. Okay? So you're going to take this positive slope and add it to the weight. So what happens is your weight increases, or in other words, it just moves right. Now let's take the other slope. Okay, the condition or the situation when you have a positive slope. So this is the case when you have a positive slope. In this case, you want to move left. So you want to decrease the weight. Again, we have our original negative sign from the slope function. And if our slope is positive in this case, that means we're going to have a positive sign right here. So negative multiplied with positive gives you negative. Okay, so you're going to subtract the slope that you have from your original weight. So if your original weight is somewhere here, then when you subtract the slope, you have a negative sign, so you're going to subtract something from this weight. Okay, and this something is the slope. So when you subtract it, your weight gets smaller and it moves to the left, which is the objective, and it reaches the minimum point. So that's the idea of gradient descent. Simply, you calculate the slope and then move in the direction opposite to the slope. Okay, now let's talk about how gradient descent is applied in neural networks. So this is what we have right here. Remember, we want to add the negative of the slope to our old weight. So this is your old weight, and now you're adding the negative of the slope. So this is the weight update rule used to update the weight of a neural network. So W here in green is your old weight. Negative here in purple is your negative slope. Remember, we're always taking the negative of the gradient or the negative of the slope. And here is your learning rate, which I'll be describing right now. And the gradient here is basically the slope that you calculate right here. So this is the derivative of the loss with respect to the weight. Now let's talk about the learning rate. Now the learning rate is how fast we're updating the weights. In other words, it's the step size of the update. So let's say that you're on this point right here. And now you calculate the slope, and the slope is very big. Now, if your learning rate is also big, so let's say it's just 1. So you're going to take your weights and subtract the gradient from them. Okay? So when your gradient is big, what's going to happen is that you're going to jump to the other side of your loss curve. Okay? So this is the loss curve, and if your slope is very big, then you're just going to jump right here to the other side. And now again, you do the same thing, you update the weights, and again you calculate a very big slope. So in this case, it's going to jump right here. And then you reach here, so what happens is you calculate the slope, and again the slope is very big, and you end up jumping to the other side right here. Recall why we're jumping to the other side is because if the slope is positive, that means we want to go left. But what happens here is we go left too much. So we go all the way until here. So the weight is going to be somewhere here. And when you add this huge slope, you're going to go to the left, too much to the left. So you're just going to end up going to this point right here. And now we have a negative slope, so we want to move to the right. And again, if your slope or gradient is very big, then you move to the right too much and you end up somewhere here. Again, now you want to move to the left, so you calculate the gradient. If your gradient is very big, then you end up moving to the left too much, so you end up on this point right here. So in this case, you might never reach to this minimum point because you're just jumping around. So what a learning rate does is just limits the step size. Okay, so if you're on this point, then when you multiply the gradient, which is going to be very large, with your learning rate, then rather than jumping here, you're just going to jump to a point down here. Okay, so it limits your gradient, it limits your step size. So this is an example of applying gradient descent with a big learning rate, and this is an example of applying gradient descent with a small learning rate. As you can see, the step size is very small right here, and through several iterations, then you'll reach this minimum point. So this is the weight update rule with learning rate.